friend and now collaborator, David Spergel, mentor of mine. Just this morning I was flying back from Arizona State, where I was yesterday. And then on the plane, Southwest Airlines, so they kind of goof around, right? And the pilot gets on, and he sounds like Chuck Yeager. He's like, well, we're going to fly north-southbound. We're going to head over to beautiful San Diego. And he's channeling Chuck Yeager. And there's an expression every pilot, I'm a pilot, you guys know that, every pilot secretly tries to channel his inner Chuck Yeager when he flies, or she flies, as the case may be. And I'm thinking, this kind of applies to David. David is sort of the astrophysicist that all of us aspire to be in some way or another. He blends a very deep understanding of experimental physics, which he'll talk about, even though he's not an experimentalist. He has made fundamental contributions to experiments that have been among the most, if not the most, highly cited works in all of science in the past few years, namely the WMAP satellite results. He has played a foundational role currently playing a role in the WFIRST telescope project, and is legendary for a slew of awards and honors that I don't have time to mention, but they include the MacArthur Award, and he won the Breakthrough Prize last year, and shared the Gruber Prize, many other accolades and awards. But I really think it's the personal touch that matters, most when I think about David. It's really his students that matter. He was telling me, as he often does, about how many letters of recommendation that he's written and will write. And it just occurred to me that I think the hardest thing in the world would be to write a letter of recommendation for David. It would be impossible to write one for you, and just the exercise of it, I don't even know if anyone could do it. But you've done so much for astrophysics, for us personally, and we're really pleased to have you here today. And you'll be giving 2 talks, one now over pizza, and then again at 3 o'clock, talking about a project that David's involved with, in part due to his role as the founding director of the Flatiron Institute, which is sponsored by the Simons Foundation, of the Center for Computational Astrophysics in New York City, and they have many, many wonderful community-wide events, and if you ever get a chance to participate, you should take advantage of it. So we're really honored to have David here today. Thank you, David.
Great. So thanks. It's a pleasure to be here. I've been promising Brian to come for a while, and I'm really glad I finally got here. What I'm saying a bit about my addresses. So I'm now splitting my time between Princeton and Flatiron. Most people have heard about Princeton, so I'll try to describe Flatiron. So this is a brand new institute. In fact, the construction completed between when I left on Friday and today. So I called some people last night, and they said, oh yeah, the cafeteria is great. I was like, oh, it's opened, and we now have the auditorium. Excellent. So things are moving quickly. I haven't been gone that long. I just left for a couple days, and things change. What we are, we're supported by the Simons Foundation. The 0th order version I describe to people who haven't been there is it's 4 Max Planck institutes on top of each other. There's the basic research institutes. One focused on computational biology, another on computational quantum materials led by Antoine Georges, one on, we just started last month on computational mathematics that will be led by Leslie Greengard, cover things varying from visualization to algorithms, applied math, machine learning, statistics, that whole spectrum of computational tools that we all use, and then the Computational Astrophysics Center. And we're structuring it in a way in which we try to be really embedded in the New York area. We have only now, I guess, we have 58 people there right now, 9 of whom are on permanent appointments of various kinds, or part of our research staff. The next 12 are joint appointments with surrounding universities. So we now have 2 joint hires with Stony Brook, 3 with Columbia, 1 with Rutgers, 1 with Penn, 1 with Museum of Natural History, 1 with Princeton. Most of those joint hires are at the assistant professor level. So there are these assistant professorships where they're spending half their time with us and half their time at their host university during their first 3 to 4 years, and then go full-time at their university and then spending the summers with us. So they have reduced teaching load, and everyone seems to like this. The new faculty member gets less teaching, and the university gets to pay only half the salary, so borrow against retirements. And by the time the bill comes through to pay for the new faculty line, you're on to the next dean. It's their problem. So it's been working. We're doing another search this year for a position, and I anticipate doing actually 2 more the following year. There are these joint assistant professorships, and then we've got 25 postdocs and have 8 sabbatical visitors. And so and a lot of those people sabbatical visitors are drawn from the region. So we're trying to connect the greater New York area and really make it a center for computational science more broadly. We're part of the Simons Observatory, working with Brian and Cam, and Raphael was here on that. But we're also really trying to be a center for a convening place for astrophysics. So we've had 2 workshops in the last year. So there's sort of always a meeting going on. And I hope some of you have the opportunity soon to come out and see us there. So let me now transition to my talk. Okay, good. I don't want to pull something down as I jump around with the wire. What I want to do today is give at least my sense of where we are in cosmology. And I think it's a very interesting moment, because in some ways, our modern cosmological program has been remarkably successful. We have this simple model, some fundamentally 5 basic parameters that seem to fit or nearly fit all the observations. The challenge is that nearly. The data is getting better and better, and there are intriguing tensions. And those tensions, the theme of this talk will be to sort of review these tensions, give you my take on them, and then look to how we might make some progress on this, both observationally and in terms of theory. So first, to start with this plot, and this is actually from the Planck 2013 paper. The 2018 data for temperature looks the same at this level. And to me, this is just this remarkable success, both for experimental cosmology and theoretical cosmology. I think the first thing to notice is you have on this plot 4 experiments, completely independent, making measurements of microwave background fluctuations at the microkelvin degree level, and basically agreeing. And here's the WMAP data, the Planck data, where out to about here, where the WMAP is cosmic variance limited, they agree almost exactly. And in fact, when the calibrations were all done properly, they're very consistent. And then out at the high multiples, you have the ACT and the SPT data. My own experience of this was just incredibly wonderful and exciting in that we would fit the data. We had fit the data to the WMAP 1-year model, and we tried to be pretty systematic in not changing things and not really looking at the cosmology till we froze the maps. We'd freeze the maps with the 3-year data, and we'd run the power spectrum. And you'd watch all these points out here. They were kind of all the points that were 2 sigma off, that could have pointed to some problem. The data gets better, and they kept sliding to the line. And then you'd have it's a little bit off here, and the 5-year data comes in, or the 7-year data comes in. And, I had the great fortune to be the person who got to run the code the first time, and you actually watch the points go zip, zip, back to the line. And then things came in on the ground consistent with this. Planck came in. All these pieces just come together remarkably well. And then it's not just the temperature that temperature fits well. It's now things like temperature polarization. And this is from the Planck 2018 paper. And I believe in this plot, the model is fit to the temperature data. The model, when you're doing the fit, doesn't know about the polarization data. And then you can compare it to the measurements of TE, the measurements of EE, and the lensing measurements. And lensing measurements are telling us about the amplitude of fluctuations, typically around redshift of 2. And, you know, sometimes I think you look at these plots and would say, okay, for this type of cosmology, we're done. Well, if that were true, I would not be giving this talk. You know, and we wouldn't be, I think, interested in pushing further with things like, as we'll get to, the Large Aperture Telescope, with Simon's Observatory. It's also one of the motivations for me for projects like WFIRST, because one of the lessons that I take from the story we're about to go through is when we do these kinds of measurements, ultimately we are limited not by statistical errors, but by systematic errors. And I think, for me, one of the drivers in the design of Simon's Observatory, but also in the design of WFIRST, is we want to measure things in ways in which, if we see something interesting, we see something that differs from expectations, that we can get up and say, this is new physics, rather than say, well, there's some systematic errors we don't understand. All right, so what happens when we go to low redshift? And in many ways, and I'll come back to this at the end of my talk. Let me just say, right on the board here, we'll come back to this. What are we actually measuring when we measure these parameters?
What's the wire?
Yeah, actually, I don't think the microphone's working, so.
This is working.
It's working.
That one's working. I don't think you need the loud mic.
I can move this.
No, just take off the loud mic. It's not working.
Is this fine?
Yeah, you can go.
You don't
Okay.
won't trip.
Let's safer.
Unlike last week's speaker, who's God rest his soul.
So I gave this talk at the IAU meeting in Buenos Aires that people who were there still remember, even though it was 14 years ago. I was talking on the WMAP-1 results, and there was a gap. It was on a big platform, 4,000 person hall. There was a gap between the hall and this raised platform, and this was up here. And as you probably have noticed already, I walk when I talk. And I gesture like this to point to a data point. And what I didn't realize is there was a hole here. And I then fell slap. And to the people in the audience, they just saw me disappear. And they had no idea whether I fell 3 feet, which I did, or 40 feet. So I then knew like I fell, it hurt. I was like, all right, I'm not going to let this interrupt the talk. I'll jump up and just keep going. And, you know, there are people in South America who, like, that's what they remember about me. Okay, so I think about this stuff not in Fourier space, but in physical space. I think the way to think about what you see here is if I start out with an overdense region that has an overdensity of baryons and photons and dark matter. The dark matter, which is black, stays there. And the baryons and photons propagate out as a sound wave. And if there was no photon diffusion, this would be completely sharp as it propagates out. But because of photon diffusion, you've got a cold spot here and a hot ring here. And the thickness of this ring is determined by photon diffusion. And this power spectrum on top is nothing more than the Fourier transform of this. Remember, it's a ring, right? So you have a characteristic wavelength that sets the first peak. That characteristic wavelength is equal to the distance the sound wave moves. To be more precise, RS is the integral CS dz over h of z from beginning of the universe to decoupling. And that's effectively what we're going to measure. The angle we see associated with the fluctuations, the angular scale associated with that peak, is RS divided by the angular diameter distance. So this is how I measure the Hubble constant, is I know this and I infer this. And the way we measure things like, how do we measure the baryon to photon ratio from the CMB? Well, if there's more dark matter, more baryon to photon ratio I get through the thickness here, right? There's going to be more, as I change that, the amount of diffusion changes. That changes the silk damping. It also changes the ratio of the first to second peak, because it changes the height here. The ratio of this term to this term is going to depend on how much dark matter there is. And that sets the height of the adjacent peaks. And the fact that you've got this, you're taking the Fourier transform, remember this is a circle of something with negative here or plus here, is why the even peaks, which go up, down, up, are lower, and the odd peaks are higher. So all of that really just comes out of that picture. And you can see from this that the basic parameters, right, the baryon to photon ratio, the baryon to dark matter ratio, are all coming out of this structure here. And a reason I wanted to point this out is I want to come back to this at my end of the talk and say, okay, if things aren't fitting and the data's right, what do we have to change? And the bottom line of my talk is we're going to have to do something either to this term or this term. We're going to have to do something to the expansion history of the universe. And that means, and since the Friedmann equation relates it this way, it says there's something different about the composition of the universe than we're assuming. And that's going to be the bottom line of the story, is if at the end of the day it turns out not to be systematics in one or more of the data sets that I'll be talking about, we're going to be driven, because it's such a simple argument here, to changing the properties of the universe.
You could presumably also change the speed of sound.
You could change the speed of sound, but that's, I think, even harder to do.
Yeah, you can play with it.
You can, Now, you can, something that looks like changing the speed of sound in a way, because I haven't told, there's the effects of neutrinos, which free stream and shift the peak around. So that looks a bit like that. But you're stuck with pretty simple things that you have to change that are pretty fundamental. So here's measuring this ratio. So this is what you'd expect when we do things like BAO measurements. We're keeping this length the same and looking for the BAO peak. And now measuring the angular diameter distance to features in the galaxy clustering spectrum. Remember that the same physics that puts the feature in the CMB, the fact that we've got these extra baryons and photons, puts a characteristic length in galaxy clustering. So when you look at the galaxy correlation function, C of r times r squared, there's this peak at the sun horizon distance. And since we know this peak location, we can again measure the angle on the sky associated with the peak in the galaxy correlation. And that's really what these surveys are doing when they're measuring the distance as a function of redshift. And for most of these surveys, things look very consistent, particularly with the small error bars from BOSS that really forces things to fit quite nicely. And if, again, if we just had BOSS and Planck, all the pieces fit together well. Now there isn't a little disturbing point out here. The distances you get with Lyman alpha forest, distances to redshift sort of 2 to 3 range from BOSS is about 2 sigma off.
So does this constrain W to be -1?
This would constrain W to be -1.
So you know it to within 5%.
From this particular data, about 10%. You can also add in the supernova data that helps constrain W. And the supernova data, if we don't know the absolute, they're very good standard candles, but we need to standardize them. If we standardize them by using the BAO points to measure the distance to redshift 0.5, and then calibrate here, the supernova actually is very nicely on this curve. The fly in the ointment, and one of the flies in the ointment, I'll talk about some more as we go on, is the local measurements of the Hubble Constant. And they're up here. And it either says there's something wrong with these measurements, but the groups involved have worked pretty hard, and I don't think anyone has been able to identify, here's something wrong in the Cepheid distance ladder, you redo this, you'll correct it. Or you try to do something like, let's change this curve to go through those points. Doing that, making h of z change rapidly, means the density of the universe has to be growing with time rapidly. It requires an equation of state with W less than -1. In fact, gives you a universe that's being torn apart in the Big Rip. So when I give my popular talks on this subject, I always, I often tell the story of, almost 2 years ago today, I was interviewed by the notorious magazine New Scientist. And they asked me what I thought about the Big Rip, and is it consistent with the data we have? And I said, well, like the idea of a Trump presidency, the Big Rip was consistent with the data we had and frightening, but I didn't think either was going to happen. I told that joke up in Santa Barbara last night, but 2 nights ago. I gave a popular talk at University of Southern Mississippi a month ago. I decided not to use that. No, in fact, when I went to dinner with the faculty, it turns out, of course, at a place like University of Southern Mississippi, you can't find a more liberal group than the faculty sitting in a place, little bright islands of blue and seas of red. And the Lyman alpha stuff is, one of the points that's off. There's this funny, when you the idea that everything fits only works really well when you combine both data sets. So this is what happens from the galaxy BAO for omega matter and H0. This is from a paper from Addison and collaborators. This is the Lyman alpha. You combine them together, everything fits beautifully on the conventional value. And this is one of the points that's sort of off by 2 sigma. That's, and I wouldn't pay too much attention to this until if it wasn't for some recent data that's come in. And one of those data sets that I think are worth paying attention to are the gravitational lensing measurements. And this is work by Sherry Suyu and collaborators with the Holy Cow lens sample. And this is a very nice way of measuring H0. This in some ways, before we were talking about doing this from the CMB, this was going to be the clean way of doing cosmology, right? Because what you're going to do is you measure your time delay. That gives you one length. You know the velocity dispersion of the galaxies in the lens system. You measure that. And then given the time scale and the lens angle, the angle of the system, that gives you the Hubble constant. And now they've done this with the sample of 5 lens systems. And in their most recent combined measurements, they're bang on the Reese value with pretty small error bars. And this is from a paper from earlier this year by the Holy Cow team. And these data will continue to get better, and this says, well, maybe we should take this seriously. The other thing other results that intrigued me recently were when the dark energy survey.
Sorry, David, can you go back? I mean,
Yep.
are those other data? I mean, it looks like they're just multiplying likelihoods together.
They're multiplying likelihoods together.
Is that kosher? I mean, presumably they're they're using similar types of techniques.
Well, but the errors are statistical,
They're totally similar.
right? Is the claim? So the errors are the claim, and
They're not very impressive. I mean, if you look at the blue curve,
No,
for
the
some
individual ones are not. The errors are pretty big, right? You can see the uncertainties. In the modern age, uncertainties plus or minus 5 on the Hubble Constant are impressive. They once were very impressive. But the claim is, and again, this requires is not a common systematic in the methods, right? And you worry that about systematics historically. I remember Paul Schechter getting up and giving a talk and saying he could guarantee the Hubble constant was less than 50 based on time delay. And he was so confident of this. And it relied on the fact that he made very restrictive assumptions about the mass profile. And they've certainly kind of learned that lesson in this field. And they marginalize over those uncertainties. And, you've got, with these multiple lens systems, lots of constraints. This is a technique as a whole that I think is worth paying attention to, because with things like LSST coming, we're going to have an incredible number of strong lens systems. And with ability to monitor things, these kinds of techniques may turn out to be, this is already competitive and will be quite interesting. Another data set when it came out that both intrigued and amused me was the DES data. And they did a beautiful job. It's wonderful measurements. And when you take the DES data and combine it with Planck, you get this error ellipse here. And this is their best fit value of the Hubble constant. When you combine the data, is around 70 something, 72. With a W, about minus 1.4. If you look at here's the marginalized likelihoods on W. If you take Planck plus DES, which is, in some ways it's some of the two best data sets we have, W differs from minus 1 at more than 4 sigma. And this is something that you read the paper, they say it here, they don't put it in the abstract, right? And it's kind of like, wow, you've made the greatest discovery. And but it's because when you take it and now add in the BAO data, the value goes right to W minus 1. Now, a lot of this is because the BAO data plus Planck is so restrictive that this is the error ellipse you get from Planck plus BAO alone. And then you add DES, and this has a fairly big error ellipse. Right here's the DES year 1 data projected in this plane. And it just stays the same way. But this is showing that there was real tensions there. This is just zooming in on the plot. And I must admit, I would, when I hear a talk from DES people earlier this year, I would always say at the end, what's going on here? This is Planck plus DES. This is Planck plus DES plus BAO. Data shouldn't, I'm adding one extra data set and it's shifting by 3 sigma. There's something not right here. Then I found myself as part of the HSC team looking at our data. And here's some HSC, the first results that came out from HSC. Let me say a little bit about Hyper Supreme Cam. This is a 1 square degree camera on the Subaru telescope. We're carrying out with this a survey that's covering less sky than DES, but 2 magnitudes deeper. As a result, we have I think in this analysis, about 16 galaxies per arc minute squared, so much higher galaxy density. And this first analysis, which uses only 136 square degrees of data, our limits on parameters are as good as the DES year one, which is more area. And we will have comparable limits as time goes on to DES. It's a collaboration between Taiwan, Japan, and Princeton. One of these things is not like the other. It's a very nice stepping stone to LSST, because in some of the regions we're getting to LSST depth. And you get to see, one of the challenges for LSST will be confusion limited. Well, when we looked at actually I'll go to this plot because it looks so identical. We were very good, we blinded our results, so we didn't see things to the very end. So kind of a couple weeks before we unblind, we look at parameters, and here we are, and I look at our figure in our new paper, and there it is, we have the exact same thing. Here's HSC plus Planck. Here's HSC plus Planck plus BAO and the supernova. It was really BAO that drives it the most. We have the same value, same error bars, same type of discrepancy. And you can see that why that comes from if you look at the sigma 8 omega matter constraints from the different surveys. So this is the amplitude of fluctuations, the density of matter. There's a linear combination of the two, which is basically the amplitude of lensing fluctuations. That's what you measure very well in these surveys. And here's where we are with HSC, and here's the DES wider. Here's data from the KIDS survey, a European survey led by Konrad Keuchen. And these are they're all consistent with each other. And here's the Planck result, which is a bit high. And it's the fact that you've got the Planck result pulling on it. You can see it even more in that projection. You can see that they kind of marginally overlap. That's what's driving this sort of tension. Now it's a tension. This isn't 5 sigma off yet. But all of these experiments, HSC and DES and KIDS are pretty independent. There's different pipelines, certainly different parts of the sky, and they're all giving values that are low. I'll note, by the way, the old WMAP values fit perfectly with everything. But so one way of looking at what's going on here is that here's the HSC value. This is from the HSC paper. You can see that the CFHT and KIDS and HSC measurements are all consistent, and the Planck value is high. And the errors on these are such that they're not off by so much, but if you start adding the errors, it starts to look intriguing. And as I'll show, I'll get to it in a moment, this is all consistent with the Hubble constant being off.
Are those error bars 1 sigma?
Those are just 1 sigma error bars. So you combine them, but they're off by, the values are off about 2 sigma when you look at each of them. But there's sort of 3 experiments, each off by 2 sigma. That's why this could go away, but there are more and more things that go the same way. So this is another way of measuring the amplitude of fluctuations, which is using clusters, SE clusters and SE cluster counts. When you go from the SE cluster counts to putting on cosmological constraints, we need to know the relationship between the SE mass and the SE signal we infer and the mass of the cluster. Because if things were in perfect hydrostatic equilibrium, then the SZ mass will equal the total mass. In order for the Planck data, the number of clusters seen in Planck to be consistent with the fluctuation seen in Planck, clusters must be underluminous in SZ. That the SZ mass that we infer, which is basically the amplitude of the sigma Y signal, has to be, this is just the notation used in the field, unfortunately introduces yet another term for bias, where it's bias. The SC mass has to be about 60% of the true mass. And if the SC, what we expected to see in Planck was an SC signal that was brighter and hence more clusters, and that's not what we saw. So this gray value is what you expect to see in Planck. The points here are different groups calibrating what the relationship is between the SC signal and the true mass as a function of the SC signal. And the way they do this is through weak gravitational lensing. You take the SC clusters and you stack them, and you measure the weak lensing signal of the galaxies behind it, and that gives you an absolute calibration.
Can what's going on in clusters, like cooling flows and all that, affect B?
That affects B. That's why B might not be. That's why B might not be 0. And you want B to be 0.6. But the nice thing about this calibration is you say, I don't care about cooling flows. I'm just going to observe this on the sky and say, what's there? And, you know, these are a bunch. Here's this particular paper was combining HSC data with the ACT clusters, only with 136 square degrees, and I think there are 8 clusters. And again, everything's sort of 1 sigma, 2 sigma above where it should be, if you want everything to fit. All of which point to the amplitude of fluctuations. If I simply took these numbers and said the value should be more like 0.7, 0.75 for 1 minus b, that would give a value of sigma 8 consistent with the weak lensing experiments. So everything is pointing to a sigma 8 of about 0.78 rather than 0.83. You know, and these, again, all these error bars are, you know, these are all sort of independently 1 or 2, sort of 2 sigma off, but there are a lot of experiments, a lot of measurements with different clusters. And this is something that's going to get better quickly. Right now with ACT, we have about 20,000 square degrees of data with a very large, much larger cluster sample that overlaps HSC. And we're in the process of redoing with a sample that I think is 5 times larger, these points. And those error bars will shrink, and either this will be like what happened with the CMB power spectrum, and as the error bars get smaller, things shrink back to everything fitting, or we'll see an interesting discrepancy. Now, one of the reasons all these things go the same way is when we measure things in the CMB, we're actually measuring a combination when we look at these ratios, that what we measure best is roughly omega matter Hubble constant cubed. So we have a very good constraint in this direction. So if the Hubble constant was actually 72, that would imply a lower value of omega matter. That means that density fluctuations don't grow for as long, because if omega matter is smaller, we make the transition to dark energy domination sooner. So that means a lower value of sigma 8. So if, we only use, and this shows the different cuts on the Planck data set. So here's WMAP data only, Planck data at L greater than 800, Planck data at L less than 800. This is the fiducial measurements. You do everything from here. Right? That's the Hubble constant of around 68. But you can see if we just took low L data and use the best value from low L data from Planck, that would give a lower value of omega matter, a lower value of sigma 8, a lower value of the Hubble constant. All the pieces would fit together. So one possibility is there's something subtle that we haven't seen yet and figured out what is yet in the Planck data, and there's something going wrong in the high L Planck data that's pulling things up. And I'll show you later how subtle, how small that could be. So what's going on here There could be systematics in the astronomical data. We almost always underestimate our errors. Could be in all these experiments. And, most excitingly, it could be that the data is going to be torn up in a big, universe is going to be torn up in a big rip. We need more data. So one step in doing this, and I'll talk about what we're doing in our current analysis, is data from the Hubble Cosmology telescope in Chile. There's our ACT collaboration team list. There's some of the people there. And just to give a sense of what the data looks like, here's a Planck map, and with ACT we're zooming in at higher resolution and higher sensitivity. And to show you what we're trying to measure, these are two plots that scare me tremendously when we think about what we do with CMB measurements from Simon Aiola. He's multiplied the usual power spectrum by an extra factor of L, which tilts it up a bit, keeps things flatter in the range you want to look at. This is the current data. There are two lines here. The dashed line is a Hubble constant of 72. The gray line is a Hubble constant of 68. With, moving along that degeneracy line. So the dashed one is about 3 sigma off the Planck data when you go through all the data and all the points. But it's off because everything's slightly higher. So that means that to do this right, you've got to measure your beams and your transfer function to exquisite precision so you can tell the difference between these two. And we like to, and in many ways CMB is a very clean way of doing cosmology. But this shows you the kind of precision that we need to do the experiments at to get the kind of precision cosmology that we're doing. Now the effects are a little bit better in temperature polarization. So here's the two things in TE, and you can see, particularly around these peaks, that's the low is gray, yeah. Low is here, high is here, low is here, high is here. So it's actually about, around the peaks, almost a 20% difference at the high peaks in TE. So that's one of the reasons you can see why TE is good at doing cosmological parameters. And what we will be doing, what we have already with data in hand from ACT, is much smaller error bars than Planck in this region of the plot. So we'll be able to get an independent measurement of the Hubble constant. And right now we have all the data in hand, we're finalizing the beams, but I can't tell you what answer we're getting because we're trying to do a blind analysis. So we have a plan and we're going through the null test. We don't want to be biased because some of us would really like to piss off George Estafiew and get a value inconsistent with Planck. And some of us would really like to piss off Adam Rees. And the rewards are you win either way. Here's some of the folks gathered as we're doing this. And the point is, well, it's nice to see the people working on this part of the pipeline, but in the back is all the tests that we want to go through, and we're now, mostly through them before we open the box effectively.
And inside, you see a UCSD alum, Steve Choi.
Yes, and who's doing a ton of the work. He's one of the real heroes of the analysis. In fact, if I were to say who has done most all the way along the way. Now, moving beyond, and this next 4 slides truly represents bringing coals to Newcastle, because now I'm going to talk about what we do next, and this is talking about the Simons Observatory. And not only is Brian the PI, these are his slides that I stole from him.
I stole them from somebody else.
That I then, as I put together talks, use as sort of the overview slides. And, the exciting, exciting for people like me who are working with work with the data, but scary for Brian and Cam and others, is that we're going to be on the sky. We're planning to be in the sky in 21. 21 is really soon. So, things are moving along. Here's a picture of people gathering here in San Diego for one of the team meetings. And here's where we'll be. Right, so here's the Simons array and ACT. And the Simons array has really two pieces, right? One is the large aperture telescope, and the other is the small aperture telescope. The small aperture telescopes are focused on going after gravitational waves, going after what we see on large angular scales. That's an incredibly exciting science program. But but for the purpose of my talk, the exciting science is in the large aperture telescope, because that's going to measure that TE spectrum you saw on the EE spectrum you saw to really high precision. And when we look at the science goals in the program, a lot of this stuff here is coming from the large aperture telescope. And one of the things that we will really weigh in on is, with real precision, is what these cosmological parameters are, right? If you go, I should advertise it here. There's a really nice paper for those who want to see the details.
Next slide.
Next slide, yes. There we are. Oh, it's a build.
Just guessing.
It's a build. Yeah, there you go. I'm usually not so high tech to use a build. I just put everything on one slide and go tease. Right, that paper on the archive nicely goes over some of the sensitivities that we'll achieve in these parameters. And we will go after it actually in multiple ways, right? So not only will we measure the parameters through getting accurate characterizations of what's going on with this physics that let us get at these ratios, but we'll also be detecting large numbers of clusters and have a precision lensing signal. So our measurements of lensing of the CMB will be more precise than any of these lensing data I've shown to date. And we'll be able to calibrate our clusters from lensing of the CMB to high enough precision that will provide yet another independent measurement of signature. So, one or two things will happen in the next 5 years, which will be very exciting. Is either we will find, as our data improves, that the pieces actually fit together. A lot of these discrepancies are sort of 2 sigma if you believe the errors from Reese's group. They're like 4 sigma. That those will go away, or we'll see they'll point to something new. And to go back to just remind people of what I wrote there, what we're measuring, if it's coming from the CMB, is really fundamentally just these ratios. And I've got to either change something here or something here. And it's actually kind of hard to change something here, because if I want to just change this piece here, this changes the local measurements. And this is going to change the BAO and supernova distances. So if those BAO and supernova distances are right, they pin down W, they pin down H of Z. And they don't, we don't get to just freely play with this function to redshift of 1,000. We've got lots of data points between here and redshift 0.5 and 1 and 2. So we've actually evaluated this interval at a bunch of different places. So in some ways, this is a hard one to change and fit the data. And if we change this one, where most of this contribution to this interval is coming from stuff close to ZD, it's coming from stuff around redshifts of 1,000 and 2,000. This is temperatures of 3,000 Kelvin, 6,000 Kelvin. This is effectively adding new physics where we think we know what's going on. And there are ways to do this, and people put in things like neutrino interactions and stuff like that. But if it turns out to be something here, all this is pointing to something exciting new that we can learn. So let me just leave it there. I don't have an answer, but this is one of the things that I'm really excited about in cosmology, because we've got an interesting problem, and we're going to make progress on it. So let me stop there.
So if George Ford were here, he's discussed for 3 hours or something crazy like that. I know that he had concerns about the way Planck was handling their neutrino physics. And I don't know if that's been resolved to, say, George's satisfaction, or if that applies to the high L data in particular. I just don't know enough about it, but maybe you or somebody in this room knows what I'm getting at.
So the neutrino physics does affect the high L data, right? So that's, what neutrinos do. Neutrinos free stream, and they sort of give their distribution looks something like that. And this assumes neutrinos are not interacting with free streaming, and they exert a gravitational pull on the baryon photons, and they also create a gravitational potential that affects the fluctuations. So the neutrinos actually shift the phases of the higher peaks, and they sort of don't change this overall shape much, so they don't affect the low peaks, but they do come in at the high L. And I actually don't know what piece of physics he thinks Planck is missing. So I can't,
Somebody else in the room?
Yeah, well, he's looking at models with sterols and then arguing that there could be new physics in there which looks like a sterile neutrino, which isn't. Right? But if you just take those neutrinos as we know they exist, Planck has everything in there.
I mean, so, but I think he's right, in that if you want to look for places where you're going to change the physics and change things, the neutrino sector is important at this redshift. Neutrinos are about the same, 15-20% roughly of the energy density of the universe at this point. So order unity changes to the neutrinos by adding a next family that's sterile, adding interactions, things like that. As you could see from the plot I put up, you don't need to change the power spectrum very much to shift the Hubble constant. It corresponds, actually, if you meant to express it this way, to about 5 to 7% change in this distance here, of the value of that integral equivalently, is what you need to shift the Hubble constant from 68 to 72.
Andy?
Yeah, so if you have the time delays from lensing as a constraint on the Hubble constant, and then standard sirens from gravitational waves is another technique, if in a few years they're all consistent with the Reese et al. Supernova and Cepheid's value, what would you then conclude about exactly where the problem is with the CMB?
And at the same time, we confirm with ACT and then with SO the Planck results, right? So remember, Planck is driven mostly by temperature. The constraints for SO and ACT will be coming from TE and EE, so they're somewhat independent. If either they find something that matches Reese, in which there's something subtle in the Planck experiment, it's a hard experiment that they had missed, or they agree with, they agree with Planck, and the standard sirens should do a nice job of getting H0 locally, right? One of the neat things about the lensing that they talk about is it's actually also giving you information on H of Z, right? Because the standard sirens, where you can see neutron-star collisions with LIGO is local from a cosmological point of view. With these systems that Suyu and collaborators are looking at, those are at kind of intermediate redshifts from our point of view, so they give you points there. So, if the two data sets really don't agree, or high redshift and low redshift measurements, we're now convinced are definitely right, and they disagree. We're basically driven to changing this physics, right? And, you can sort of play around with anything you see on the board. You can change G, so you can try to, change general relativity on those scales and, come up with some alternative gravity theory. You can change the density of the universe, You know, and the neutrinos sector is one way to do that. So I think that's what we'd be driven to.
I'm going to call myself.
Great.
So, you know, most of what we do in astronomy is measure ratios between two different things, and at the base of the distance ladder, as I understand it, not being an optical astronomer of any renown, is the astronomical unit. And who's to say that we know that to better than, you know, percent precision, and
On the AU, we know really well.
better than, I mean,
The distance between the Earth and the Sun,
yeah,
it's light travel distance.
but from
Satellite orbits, things like that. I mean, there's
so
lots
you
of...
know the radius. You're saying you know the distance. I mean, from
Okay, well,
other satellites.
one way I can measure it, I don't know if this is the precision way, but thinking off the top of my head. If I know the orbit of Earth and Mars, right, and we know Kepler's
I
laws,
think they get it from Venus, but yeah.
right, I can do it that way. I can do it from, I mean, the way AU was measured first was Venus, right?
Yeah.
But I think that's because you could just measure where the transit of Venus took place on different places of the Earth.
Right.
That's the historical way. But I think right now you get much more accurate measurements from travel time to satellites. So we have man-made satellites on orbits. We know what their orbital period is in AU. We measure the light travel distance from us to a satellite, which you can do to exquisite precision. And that gives you very accurate measurements.
I'd say we had a part to the 10 or something.
Yeah.
Yeah, it's all
Then
timing,
it's
it's clocks.
It's clocks, yeah. So that one's
That's
good.
not not wrong. Is
But
it?
there's definitely uncertainty in like the LMC distance and then you know
But
the
power
lower
lines
rungs.
derived. Oh,
But
Yeah.
to advertise my talk at 3 o'clock, where I will not be talking about that part of Gaia, this is getting much better fast. Because Gaia, which will be the theme later this afternoon, is giving us much more accurate parallaxes. And then once I've got that AU, that's now giving me 10 microsecond level measurements of distances. So you can do percent measurements of a kiloparsec. And that's now letting you calibrate things like the ROLARs and things Cepheid scales. So you can pin that down much better. And one of the things that made the error bars go down in the recent result was reducing the errors in the lowest rung of the distance ladder with Gaia. So that's getting better.
All right. Well, that was a good advertisement for the talk at 3 o'clock, which will be in here as well. So looking forward to the St. David again.
Great, thanks.